Hello and welcome to lesson number 31, Complex Numbers. To start off this lesson, consider these two quadratic equations that I have written down here. The left equation is x squared minus 1 equals 0. The right equation is x squared plus 1 equals 0. If we take a look at the first equation, we can see that we can solve this equation by simply adding 1 to both sides. If we add 1 to both sides on the left side, we get x squared minus 1 plus 1 equal to, and on the right side we get 0 plus 1. This simplifies down to x squared only on the left, since the plus 1 and the minus 1 will cancel, and on the right side 0 plus 1 is equal to 1. So we get the solution x squared is equal to 1. Now what we can do is to take the square root of both sides, and when doing so we need to remember that a multiplied by a is equal to a squared, but minus a times minus a is also equal to a squared. And due to this, we do not know whether it was the plus a or minus a that was multiplied by itself in order to get a squared. Due to this, in this particular case, since we have x squared equals 1, we do not know if x is equal to 1 or negative 1, since both of those values, when multiplied together, could give you 1 as the square. So therefore, when we write down the solution, we need to say that x is equal to the plus or minus square root of 1. And that's our solution. If we simplify this, the square root of 1 is just 1. So therefore, x is equal to plus or minus 1. This is our solution for the first quadratic equation. So there's no problem there. This is a perfectly valid solution. The two values of x are x equals plus 1 and x equals minus 1. If we resubstitute them back into here, we can see x equals plus 1 gets us 1 squared minus 1, which is going to be 1 minus 1, which is 0. If we substitute x equals minus 1, then we get minus 1 squared, and minus 1 times minus 1 is 1, so this becomes 1. Minus 1 is equal to 0, which is true. So it works for both of our solutions. Let's now take a look at this second equation. You might see it's pretty much the exact same thing, except instead of a minus sign, we have a plus sign here. In order to get x all on its own, in this particular case, we need to subtract 1 from both sides. So let's do exactly that. Let's take x squared plus 1, and let's subtract 1 from the left hand side, and that would be equal to 0 subtract 1. On the left hand side, this plus 1 and this minus 1 cancel to give us just x squared. On the right side, 0 minus 1 is just minus 1. So we get x squared is equal to minus 1. Now then, once again doing the same thing, if we just use this analogy, we can see that x must be equal to the plus or minus the square root of this value here, which is negative 1. And now what? What is the square root of negative 1? What is the square root of negative number? We do not know this. We do not know this because if you consider what a square root means, a square root just means find the number that multiplies by itself to give you the number on the inside. So in this case, when we say the square root of negative 1, we're looking for a number that multiplies by itself to give us negative 1. Now this number obviously cannot be a positive number, since if it was a positive number times a positive number gives us another positive number, and clearly what we have on the inside here is a negative number, so it cannot be a positive number. Therefore, if we consider the square root of negative 1, the square root of negative 1 is not a positive number. Well, alright, then it's not a positive number. What about the negative numbers? Well, if you consider a negative number, negative a times negative a will give you positive a squared, since the two negatives will cancel each other out. So no matter what negative number you use, you are going to eventually get a positive number when you multiply a negative number by itself. So therefore, this square root of negative 1 cannot be a negative number either. Well, alright, if it's not a positive number or a negative number, how about 0? Well, 0 times 0 is just 0, so it's not possible that that is equal to negative 1, which means that the square root of negative 1 is not 0. So if you consider the number line, the real number line like this, we have 0 in the middle, we have all the positive numbers to the right side and all the negative numbers to the left side. We've established that it is not a positive number, meaning that the square root of negative 1 is not an element of this set. We've also established that the square root of negative 1 is not an element of this set, since it is not a negative number. We've also finally established that the square root of negative 1 is not equal to 0. So, it's not a negative number, it's not a positive number, and it's not 0. That means that it is not an element of the real number, since we've covered all possibilities for a real number. If a is an element of the real numbers, then a is either positive, negative, or 0. And as we've clearly seen here, the square root of negative 1 cannot be positive, it cannot be negative, and it is not 0. So that means that this thing right here, the square root of negative 1, is not an element of the real numbers. For the longest time, this issue of the square root of negative 1 not being an element of the real numbers meant to mathematicians that it was not a number. This would all change in 1545 when a certain Italian mathematician, Girolamo Cardano, excuse my pronunciation, would write a book titled Ars Magna, which means the great art. In that book, he, for the first time in writing, acknowledged that the square roots of negative numbers are actually numbers that can be used in algebra. After this point, instances of using the square roots of negative numbers started to become more common. This is because mathematicians started to accept the square roots of negative numbers as being actual proper numbers. One particular individual, a certain René Descartes, even gave these numbers the name imaginary numbers. This name is not all that flattering as it makes these numbers appear fake. They're not fake even though they're not exactly real either, in the sense that they're not actually elements of the real numbers. They are still quite important and useful. Another individual, a certain Leonhard Euler, gave these numbers a symbol. He gave them the symbol I, usually written with a loop like this. This symbol I is defined as being equal to the square root of negative 1. This now gives us a certain value that we can use to define all other imaginary numbers. This value I is our imaginary unit. From this, if we square both sides, we can also see that I squared is equal to negative 1. Using these two, we can now build up any square root of a negative number. Consider a general square root of negative number as the square root of negative a. In this case, we can see the square root of negative a is equal to the square root of negative 1 times a. Let's assume that a is a positive number, in which case, if we take this thing, we can see that this is equal to the square root of negative 1 times the square root of a. Now, the square root of negative 1, as we defined above, is equal to I. So we can say that this is equal to I, so we have I multiplied by the square root of a. We would usually write this with the I on the end because it kind of acts more like a variable in the sense that it goes after numbers. So we can have square root of a times I, and this is going to be the general form when we have the square root of a negative number where a is some element of the real numbers. So here we can see we can now expand to find the square root of any negative number. So now at this point we have the real numbers, and in addition to that we have constructed a new set of imaginary numbers. The real numbers are of course the real numbers, they haven't changed, and the imaginary numbers are just any real number multiplied by the complex unit I. In addition to this, we can have another type of number which we're going to explore next, and to do that we're going to consider the general form x minus p squared equals minus q, where p and q are elements of the real numbers, and importantly, we're also going to have that q is greater than 0. Now, if q is greater than 0, it means that q is a positive number, which means that negative q is going to be a negative number. So, if we consider this equation here, on the right side we have a negative number, and on the left side we have a square number, meaning that the thing on the inside here, x minus p, is going to be an imaginary number. If we start simplifying this thing, we can see that this simplifies down to x minus p on the left side, and on the right side, since we're taking the square root, it needs to be the plus or minus square root of negative q. Now here we're taking the square root of negative number, which of course means that it's an imaginary number, and if we simplify that down, we get that x minus p is equal to plus or minus the square root of q times I. So this is our solution. Now what we're going to do is to solve for x. In order to solve for x, we're going to have to add p, which is a real number, to both sides. Doing so, we can see that x is equal to p plus or minus the square root of q times I. Now previously in the real numbers, we just had real numbers, and in the imaginary numbers, we just had a real number multiplied by the imaginary unit. Now here for this particular number, we can see we have a real number added to an imaginary number. This type of number, which can be written as a real number plus an imaginary number, is what we actually call a complex number. In general, a complex number Z, which is usually represented by Z, not x, is equal to a plus b times I, where a and b are elements of the real numbers. Numbers of this form are said to be elements of the set of complex numbers. The set of complex numbers is denoted by a capital C with a line down it like this. So here, this number Z, which is a plus bi, is an element of the complex numbers. We would write that as Z is an element of the complex numbers like this.
Now the complex numbers here actually includes all of the real numbers as well, since all it says in the definition is that Z needs to be A plus Bi, where A and B are real numbers. This does of course mean that B could be 0, and if B is 0, this whole part gets cancelled out, leaving us with just Z equals A. Now since A can be any real number, we can see that if Z equals A for any real number A is an element of the complex numbers, then the real numbers are a subset of the complex numbers. So the real numbers R is a subset of the complex numbers. Now it is actually a proper subset. This is the correct symbol to use and not this symbol, and the reason for that is that there are also numbers that are not elements of the real numbers that are elements of the complex numbers. So now that we've defined what the complex numbers are, let's go on to try to do some arithmetic with these complex numbers to figure out how they work. But before that, let's quickly discuss two functions that we use with complex numbers to make our lives easier. These two functions are the RE function, which takes in a complex number, and the IM function, which takes in a complex number. These two functions give us the components of any complex number. The RE function gives us the real part of the complex number Z. Now in this case, Z is equal to A plus Bi, where A is the real part and B times I is the imaginary part. Now in this case, if we do RE of Z, what this function is going to output is the real part of the complex number Z, which in this case we can see is going to be A. So if you do RE of a complex number, what you're going to get out is the real part of that complex number. Now you can probably guess what the IM is. The IM of Z is going to output the imaginary part of the complex number. Now a thing that a lot of people get confused with here is the fact that IM of Z actually doesn't output an imaginary number itself. It instead outputs the real coefficient, which is multiplied by the imaginary unit to produce the imaginary component of a complex number. So what I mean by that is, if I do IM of Z where Z equals A plus Bi, the output is not going to be B times I, but rather just the B. So in this case, if I do IM of Z where Z equals A plus Bi, IM of Z is going to give me B, not B times I. So here we can see, we can break down the complex number into two real number components using these two functions. These two functions are generally used in notation in various different applications in complex numbers, which is why we're going to be using them. So now that we've done that, let's move on to doing some arithmetic with these complex numbers to try to figure out how they work. For all of these examples, what we're going to be doing is using two complex numbers, Z1 and Z2. Z1 is going to be defined as A1 plus B1 times I, and Z2 is going to be defined as A2 plus B2 times I, where of course A1, B1, A2 and B2 are all elements of the real numbers. Now, first off, let's try and figure out how addition works for complex numbers. To do that, let's first consider what Z1 plus Z2 should be. Now Z1 plus Z2, if we just write them out, is going to be A1 plus B1 times I plus A2 plus B2 times I. Now if we consider the real parts and imaginary parts here, we can see this A1 and A2 are real parts in this total number, and B1i and B2i are imaginary parts. If we group them together, we can see that this is equal to A1 plus A2 plus B1 times I plus B2 times I. Now if we factor these such that the imaginary unit in these two is on the outside, we can see that this can be factorized to A1 plus A2 plus B1 plus B2 times I. Now here we can see that addition works as you would expect. When you add two complex numbers together, you're going to get another complex number, and we can see here, if we add them together, we can write this as the real parts being added together plus the complex parts, the imaginary parts being added together. So that works all well and good. The same exact thing will of course work for subtraction, since subtraction is just negative addition. If we do subtraction instead and do Z1 minus Z2, we're going to have A1 plus B1i minus A2 minus B2i. If we do the same exact process, we're going to end up with A1 minus A2 plus B1 minus B2 times I. So we can see once again, when you subtract two complex numbers, the real parts get subtracted and the complex parts get subtracted. So addition does what we would expect, and in the same way subtraction does what we would expect. Now moving on to multiplication, if we instead do Z1 times Z2 and we consider what this would be A1 plus B1 times I multiplied by A2 plus B2 times I. Now in this case, the distributive property still holds, which means we can distribute this into here and we can distribute this B1I into here. If we do that, we can see that what we get is going to be A1 multiplied by A2, so we can do A1, A2, then we're going to have A1 times B2I, so we can have plus A1, B2I, then we're going to have B1I times A2, which I'm going to write as A2, B1, I, and finally we'll have B1I times B2I, which is going to be B1 times B2 and I times I, which is going to be I squared. So we can write that down as I squared. Now recall that I squared, as we defined up here, is going to be equal to -1. Now based on that, we can substitute that into here and say that this I squared here is going to be equal to -1. If we do that, what we're going to get here is that we get A1 times A2 plus A1 B2I plus A2 B1I plus B1 times B2 times -1. I actually quickly write that as just minus B1 times B2. Since we're multiplying by -1, we can just put that at the front anyway. So here we have minus B1 B2. Now if we start grouping the real parts and imaginary parts, A1 and A2 are both real, so when you multiply them you get a real number. B1 and B2 are both real, so when you multiply these and put the negative on the end, you get a real number. So this part and this part are real numbers. The other two parts, A1 B2I and A2 B1I, are both imaginary since they are multiplied by the imaginary unit I. If we group them, we can see we get A1 A2 minus B1 B2 as the real part, and as the imaginary part we get plus A1 times B2 plus A2 times B1 times I. So this is what happens when you multiply two complex numbers together. If the two complex numbers are of the form A1 plus B1I and A2 plus B2I respectively, then their product is going to be real part A1 times A2 minus B1 times B2, and imaginary part A1 B2 plus A2 B1 times I, of course. Now of course, once you've done multiplication, the next thing you need to do is division. So we're going to be doing that next. Let's go down here and do that. Let's do Z1 divide by Z2 and consider what this should be equal to. If we equate this, this is going to be equal to A1 plus B1 times I divided by A2 plus B2 times I. Now at this point, we can't really simplify this any further since we don't really know how to divide two complex numbers together. However, we can simplify this down further if we multiply the top and the bottom by, instead of A2 plus B2I, A2 minus B2I. Now if we do that multiplication and we multiply the top and the bottom by A2 minus B2I, we will see something interesting happen. So if we do that, we do A2 minus B2I on top and A2 minus B2I on the bottom, we can see that what we're going to get is these two multiplying together and these two multiplying together. And we know how to multiply complex numbers. If we do the bottom bit, we can see we have A2 plus B2I times A2 minus B2I. So we have one thing plus another thing times one thing minus the other thing. So as we know, if we have the form P plus Q times P minus Q, this is going to be the difference of squares P squared minus Q squared. We can apply that in this situation and see that on the denominator what we're going to have is this first thing squared minus the second thing squared. So on the denominator, if we write that down, this is going to be the first thing, which is A2 squared minus the second thing squared, which is going to be B2I squared. So we can have B2 times I whole thing squared. Now on top, if you consider what's going to be happening, we have A1 plus B1I times A2 minus B2I. Now if we apply the distributive property here, we can see we're going to have A1 times A2. So on top we have A1 A2, we're going to have A1 A2. Then we're going to have A1 times negative B2I, so minus A1 B2I, and then we're going to have B1I times A2, so positive a2b1i, and finally plus b1i times minus b2i. So we're going to have minus b1 times b2 times i, which is I squared. So we're going to have minus here, b1, b2, I squared. Now as we know, I squared is equal to negative 1. Before we substitute that, let's actually simplify this thing further, because this thing also is going to end up with an I squared in it. If we simplify this down, we can see we have a1, a2 minus a1, b2i, a1, b2i plus a2, b1i, and then minus b1, b2, I squared. On the denominator, we can see this b2i whole thing squared is going to turn into b2 squared times I squared. So we're going to have a squared minus b2 squared I squared. Sorry, not a squared, a2 squared minus b2 squared I squared. Now I squared is equal to negative 1, and in both of these cases we have negative I squared. Now as we know, I squared is equal to negative 1, which means the negative I squared would be equal to positive 1. So over here, this negative I squared is just going to turn into positive 1, and this negative I squared is going to turn into positive 1. If we substitute that in, we're going to end up with a1, a2 minus a1, b2i plus a2, b1i, b1i, not bii, and then plus b1, b2 divided by a2 squared plus b2 squared. Now, if we start grouping the real parts and imaginary parts together, we can see that this a1, a2 divided by all of this is going to be a real number, and this b1, b2 divided by all of this is going to be a real number. So these two bits here, this divided by this and this divided by this, are going to be the real component of z1 divided by z2. And furthermore, these two bits here, this minus a1, b2i and this plus a2, b1i divided by this, are going to be the imaginary parts. So if we group them together, we can see what we get is, on the left, a1, a2 plus b1, b2 divided by a2 squared plus b2 squared, which is going to be the real part, plus this bit here, which I'm going to write the positive bit at the front, and then minus a1, b2. So we're going to write a2, b1 minus a1, b2 divided by a2 squared plus b2 squared, and we're going to take the I out and write times I, and this is going to be the imaginary part of our number. So we have the real part of our number and the imaginary part of our number. Now here we can see we need the condition that this a2 squared plus b2 squared is not equal to 0, because if a2 squared plus b2 squared was equal to 0, then we would have division by 0 in both of these bits. Now, how would a2 squared plus b2 squared be equal to 0? Well, considering our definition of z2 is equal to a2 squared plus b2 squared. Now, if a2 squared plus b2 squared are both added together equal to 0, and a2 and b2 are both real numbers, the only way that this can happen is if, actually I can put if and only if here as well, a2 equals 0 and b2 equals 0. So a2 is 0 and b2 is 0 is the only way that a2 squared plus b2 squared is equal to 0, since a2 and b2 are elements of the real numbers. So what does this mean? It means that the only way that this would not work, that we couldn't divide, is if z2 was equal to 0 plus 0i. Now 0 plus 0i is just equal to 0, which means that the only way that this wouldn't work, the only way that z1 divided by z2 would not work, is if z2 was equal to 0. So here we need the condition that this would work only if, or we could say for, z2 not equal to 0. So we can see it does the exact same thing that we would expect in the real numbers. In the real numbers as well, you can only divide one real number by another real number if the denominator is not equal to 0. In the same way, for the complex numbers as well, you can only divide one complex number by another complex number if the denominator complex number is not equal to 0. So that is how division works with complex numbers. In the next video, we're going to be diving deeper into the concept of complex numbers. However, for now, we're going to end it there with these 4 basic algebraic operations on complex numbers. Before we end, however, we're going to do a couple of examples, and I would highly recommend that you, in your own time, do a couple more examples of algebraic operations on complex numbers to familiarize yourself with the concept. So let's start off with this first example. Here we have 2 plus 3i minus 4 minus I. Now 2 plus 3i and 4 minus I are both complex numbers, and we can see here we're subtracting them. As we saw above, addition and subtraction of complex numbers work as you'd expect. You add and subtract the real parts and write them down as the real part of the answer, and you add or subtract the the imaginary parts, and write them as the imaginary part of the answer. So in this case, we can see the two real parts of these two complex numbers are 2 and 4, and we need to subtract the 2. So therefore, what we need to do for the real part is to subtract from 2 4. So we have to do 2 minus 4. 2 minus 4 is going to give us minus 2, meaning that the real part in our answer is going to be minus 2. As for the imaginary part, we have 3i here and we have minus I, and we need to subtract from 3i minus I. So subtracting minus I from 3i is the same as adding I to 3i, which means that we need to do 3i plus I for the imaginary part of this number, meaning we're going to get plus 4i. So 2 plus 3i minus 4 minus I is going to be minus 2 plus 4i. Moving on to the second one, we have I plus 1 divided by 1 minus I. Now we could solve this using the formula that we found above, or we could just do the multiplication of the top and bottom by the conjugate of this thing right here, as in instead of having 1 minus I, we could multiply the top and bottom by 1 plus I and then simplify that way. However, we could also use the formula. In this case, I think I'm going to go ahead and just do it with the base principles and just multiply the top and the bottom by 1 plus I. So doing so, on the denominator, if we multiply the top and bottom by 1 plus I, we're going to have 1 plus I up here and 1 plus I down here. Now multiplying the top and bottom by 1 plus I, this is going to be the difference of squares of 1 and I. So on the denominator, we're going to have 1 minus I squared. So if I write that down on the denominator, we're going to have 1 squared minus I squared. So minus I squared. On the numerator, we have 1 plus I times 1 plus I. If we do the distribution, we can see we get 1, so 1, and 1 times I, so just plus I, and then I times 1, so plus another I, so plus I, and then I times I, which is plus I squared. So we have plus I squared. Now simplifying this down, we know that I squared is equal to negative 1. If we substitute that in, we can see we have 1 minus negative 1, and on top we have 1 plus 2 times I minus 1. Simplifying this down, we can see this plus 1 and the minus 1 cancel, and this minus 1 and this plus 1 cancel out to give us just a 2 on the denominator down here. So this minus and minus cancel to give us plus 1, and 1 plus 1 is 2. So we have 2i on the top and 2 on the bottom, which gives us just I. Meaning that if we do 1 plus I divided by 1 minus I, the answer we get is just I. Moving on, if we consider the next one we have here, we're asked to do 2 plus I cubed. Now 2 plus I cubed is just equal to 2 plus I times 2 plus I times 2 plus I. So all we really have to do here is multiply 2 plus I by itself 3 times. We could either do that, or we could use the cube formula and expand this into 2 cubed plus 3 times 2 times I squared plus 3 times 2 squared times I plus I cubed. I think we can do it in that way as well. So if we do it that way, if we use the binomial expansion on this thing, we're going to get 2 cubed plus 3 times 2 squared times I plus 3 times 2 times I squared and plus lastly I cubed. So simplifying this down, we can see the 2 cubed is going to give us 8. The 3 times 2 squared is going to give us 3 times 4, which is 12, times I, so 12I, so plus 12I. This 3 times 2 is going to give us 6, and this I squared is going to give us negative 1, so that's going to be negative 1 times 6, or negative 6. And finally, I cubed is the same thing as I squared times I, and I squared is negative 1, so we can write this as negative 1 times I, or negative I. Finally, simplifying this down, we can see 8 minus 6 is going to give us 2 for the real part, and plus 12I minus I is going to give us plus 11I for the imaginary part. Therefore, our final answer here is 2 plus 11I. Finally, we have a solution here where we're asked to solve 2x squared minus 2x plus 1 equals 0. Now this is rather simple, but it has a twist. since the roots of this thing are not real numbers. We can check if the roots of this thing are real numbers or not by using delta. As we know, delta is equal to b squared minus 4ac. Now considering this equation here, if it's of the form ax squared plus bx plus c, then a is going to be 2, b is going to be negative 2, and c is going to be 1. Substituting those into here, b being negative 2 means b squared is equal to 4, and then minus 4, a is equal to 2 here, so times 2, times c is equal to 1, so times 1. If we simplify this down, we can see we have 4 minus 8, which is going to be minus 4. So this is equal to minus 4. Since the delta here is negative, we can conclude that the roots of this thing, the solutions, are not going to be real numbers. If they are not real numbers, as we now know, they are probably going to be imaginary or complex numbers. So now, let's try to solve this equation. We know that if we have equations of this form, then x is going to be equal to negative b, which in this case is negative 2. So we're going to write negative 2 plus or minus the square root of delta, which we could either write as b squared minus 4ac or directly as delta. Since we've already found delta, I'll directly substitute that in minus 4 divided by 2 times a. In this case, a is equal to 2 as well, so here we just have 2 times 2. Now if we simplify this down, we can see the minus 2 cancels to give us a plus 2, and then the plus or minus square root of negative 4 is going to give us plus or minus the square root of negative 4, which is 2 times I, so plus or minus 2i, divide by 2 times 2, which is 4, so divide by 4. Now we can see, if we simplify this thing down, from the 2 and the divide by 4, we just get a 1/2, and from the 2i divide by 4, we get a plus or minus 1/2 I. Or we could say plus or minus I over 2. So these two are the two solutions to our equation 2x squared minus 2x plus 1 equals 0. We can see, since both of them have both a real part and an imaginary part, both of these are elements of the complex numbers. They are not elements of the real numbers since they have an I in them. So here we can see we can solve any quadratic equation if we allow for complex numbers, and in some situations we will get complex values as the roots of those quadratic equations. So that's going to be all for this video. I hope you enjoyed. I implore you to try more examples, make your own questions for yourself and try solving them. Thank you for watching and goodbye.